Assalamualaikum warahmatullahi wabarakatuh. We are from Group A. We'll present our assignment for the subject Bmkt 3533 heat transfer. So these are our group members. My name is Ali Azira and my other group members are Nur Shahira, Mira Nur Shahmina, Dayan Punaparni, and Lim Peisan. So the title for our assignment is Waste Heat Recovery, WHR in Industrial Energy Systems. In modern industrial manufacturing, massive amounts of thermal energy are generated as an unavoidable, practical byproduct of high-temperature operations, which is often lost, wasted, and dumped directly into the environment. Rather than letting this valuable energy dissipate, waste heat recovery can be implemented to capture this escaping thermal energy from an industrial byproduct stream and redirect it to perform useful work as well within the facility. By utilizing a dedicated heat exchanger to intercept the waste stream, this recovery process drastically improves the thermal efficiency of the plant, reduces reliance on external utility energy, and lowers overall operating costs. Ultimately, recovering this waste heat through various WHR technologies transforms and environmental loss into available energy source, significantly reducing the facility's overall energy consumption and carbon footprint. So the objectives for the assignment are determine thermal recovery requirements to evaluate the net heat transfer rate needed to achieve the target temperature elevation for the process water loop. Second, calculate exchange surface area to determine the physical sizing requirements of the counterflow shell and tube unit by analyzing the log mean temperature difference LMTD across the fluid streams. And lastly, to quantify environmental and economic impact SDG 7 alignment to evaluate annual energy savings and estimate the resulting carbon footprint reduction for the facility, demonstrating a direct contribution to sustainable energy systems.
So I will present about the schematic of the energy system. So this diagram shows an industrial waste heat recovery system using shell and tube heat exchanger to recover heat from hot flue gas and transfer it to water. So fluid properties, which is have a specific capacity of 4.18 kJ/kg Kelvin, so allowing it to absorb the large amount of heat energy. So for the first one is hot flue gas inlet that enter the system at the temperature 250 degrees Celsius and acts as the heat source. And then the second one, flue gas inlet enter the shell side of the heat exchanger, begin the heat transfer processes. So, and then the second one is a shell side. So shell side is where the hot flue gas flows around the tubes. Flow around the tube, and then the baffle will direct the gas flow to increase the heat transfer efficiency. So for the tube sheet, it's for supports the tubes and prevent the gas water from mixing. And then for the system, it's a counterflow, which is where the water and the gas in opposite direction for better heat transfer. So water inlet enter tubes with 25 degrees Celsius and absorb the heat from the flue gas. Preheat So for shell and tube heat exchanger, this is a main component for heat transferred from a flue gas to the water without mixing the two fluids. This system will improve the energy efficiency by recovering waste heat and reducing energy losses. Next, this is a primary mechanism, which is a convection. The first one is a convection, heat moving in fluids. What What it means is heat moving through the fluid, liquid, or gas. So in our system, outside the tubes, the hot Becquerel exhausts gas flow from over the tubes and transfer its heat to the metal surface. So inside the tubes, the cold water flows through the tubes and absorb the heat and warm up. For the second one is a conduction. So heat moving through the solid metal, uh, what is related to our system is heat traveling directly through the solid material. So the heat from the hot gas pass directly through the um, solid metal wall to reach the cold water on the other side. So this happen easily because the metal like copper, steel, aluminum, or so on are excellent to heat uh, excellent as heat conductors. So the third one is phase change, which is the gas turning into liquid. Um, Phase change about the substance changing from one physical state to another a constant temperature. So for our system, the hot bakery exhausts contains invisible moisture, which is a water vapor. When this hot gas touch the cold metal tubes, it hits the dew point and cools down easily. So the vapor instantly change phase and it turn into liquid water. In liquid water in the droplets condensation on the outside the tube.
Hi and Assalamualaikum. My name is Mira Nur Shahmina and I will be starting to present the problem statement and the calculation. So for an early exposure, I could say that a lot of useful heat in this industry is simply wasted. So our goal is to see how we can recover and reuse that heat or energy. So here are the problem statement. I could classify that this issue is very common in many factories. Even though the exhaust gas is still very hot, it usually releases into the atmosphere. By recovering this heat, industry can save energy and at the same time reduce their environmental impact. So, for this scenario, these scenarios are given to us in the assignment. So it says that an industrial bakery exhausts flue gas at the 250 degree. Currently, this heat is vented to the atmosphere. Our task is to design a simple shell and tube heat exchanger. So from this given scenario, it says that the exhaust gas temperature is quite high, the temperature, around 250 degree, which means that there is a good opportunity to reuse that heat. So we use it to preheat the water before it enters the process. So these properties are the value given in the problem statement, including the temperature, specific heat capacity, and many more. We'll use this value in the following calculation to design the heat exchanger. So these are the first question that are given. From this question, it gave the flow rate 0.5 and it asked to find the calculate required heat. So formula that we are using is Q equal to m dot, which is the flow rate, times the specific heat for water times the difference temperature. So the difference temperature here we can see that 60 minus 25 is 35 and the given flow rate is 0.5 and the specific heat for water is 4.18. So the first thing we calculate is how much the heat is needed to increase the water temperature from 25 to 60. From the question, we found that the heat exchanger needs to transfer about 73.15 kilowatts of heat. So, after determining the required heat transfer rate that I just require, We can proceed to calculate the size of heat exchanger using the LMTD method. That's all from me.
Everyone, my name is Bmkt. Next, I will present how to use the heat transfer rate to calculate the free gas outlet temperature. Firstly, we need to use the energy balance equation. Q water equals to Q gas. Then use the value of 0.5 kilogram per second and 1.05 kilojoule per kilogram Kelvin. And we use the value of Q water as calculated before, which is 73.15, and substitute the value into the equation. Then we got the change of temperature is equals to 139.33 degrees Celsius, and then we can use the value to find the value of temperature outlet free gas, which is 110.67 degrees Celsius. So next we can solve the question that assuming an overall heat transfer coefficient of 150 watt per meter square Kelvin, use the LMTD, log mean temperature difference method, to determine the required surface area of the heat exchanger. For the calculation, we cool the free gas from 250 degrees Celsius to 110.67 degrees Celsius. Heat the water from 25 degrees Celsius to 60 degrees Celsius. We can use the temperature to calculate the change of temperature 1 and change of temperature 2 at the value of LMTD using the equation there, which is change of temperature 1 minus change of temperature 2 divided by ln change of temperature 1 per change of temperature 2. Then we can get the value of LMTD, which is 130.98 degrees Celsius. And then we can use the equation surface area equals to heat transfer rate per overall heat transfer coefficient times LMTD, and then sub the value. Finally, we got the surface area equals to 3.7 the 2 meter squared. The surface area of 3.7 the 2 meter squared prove that our cell and tube design is highly practical and space efficient for the bakery existing layout. That's all. Thank you.
Alright, with the given information and the calculated temperature hot output, we can do a graph of heat exchanger for the counterflow. So the blue arrow represent our hot flue gas on the shell side. So it moves from the position 1 to the position 2, and we can see the temperature is decreasing from 250 to 110.67 Celsius. This happened because the flue gas is continuously losing its thermal energy as it passes through the heat exchanger. And the orange line represent our cold processed water inside tubes, and it moves or enter from the position 2 to the position 1, and the temperature is increasing from 25 to 60 Celsius. This happened because the water is continuously absorbing the heat released by the flue gas. So we can see here both arrow moves at the different direction. This is what it means by counterflow. So when this happens on the heat exchanger, it will maintain a high and uniform temperature difference throughout the entire length of the exchanger and allows heat transfer to happen continuously and efficiently from start to finish.
Hi and Assalamualaikum. I'm Dayanku Nur Farhani Azrina binti Basri. Next, I will present question 4. So for question 4, we calculated the annual energy savings achieved by the waste heat recovery system. Based on the heat transfer rate obtained earlier, which is 73.15 kilowatt, and the bakery's operating hours, which is 2,400 hours per year, the system can recover approximately 175,560 kilowatt hours of energy per year. This is significant because the recovered heat can be reused to preheat processed water instead of being wasted through the exhaust gas. As a result, the bakery requires less additional energy for heating, improving overall energy efficiency. Next, this project supports Sustainable Development Goal 7, which is affordable and clean energy by promoting more efficient use of energy. Rather than allowing useful heat to be lost to the environment, the system recovers and reuses it within the process. This reduces energy consumption, lowers food requirements, and helps reduce greenhouse gas emissions, making the operation more sustainable. So, to conclude the project, the proposed heat exchanger successfully recovers waste heat and converts it into useful energy for the bakery process. The system improves energy efficiency, reduces operating costs, and minimizes environmental impact. Overall, this project demonstrates how heat transfer engineering can contribute to both industrial performance and sustainable development. So that's all from us. Thank you.